Excavations of new harbors, big dams, canals, passes through rugged mountainous terrain. These and other massive, imaginative, earth-moving projects may soon be ours, created in seconds with the tremendous energy of the peaceful atom. Nuclear explosives for large projects that are simply not feasible with conventional methods and at considerably less expense. Scientists and engineers today are carefully working toward these goals with a series of nuclear excavation experiments designed to increase their knowledge and skills in this exciting new concept. They call their program Plowshare, and the emplacement and the detonation of a nuclear explosive is only the midway point in each succeeding project. Before any nuclear detonation, the project is first thoroughly explored and proven in exhaustive theoretical analyses, researched and tested in laboratory mock-up, and often tested again with conventional chemical explosives in the field. The detonation itself serves to refine the predictive capability and to provide support data for the next related experiment. It is a deliberate, careful, scientific program. A prime example of the accuracy of these pre-shot calculations was the experiment called Sedan, detonated within the Atomic Energy Commission's test site in Nevada in 1962. This was a 100 kiloton experiment equal to the explosive energy of 100,000 tons of TNT. The depth of the crater was 323 feet. The radius, 608 feet, well within the predicted range. While Sedan represented a significant achievement, both in pre-shot calculations and as a practical demonstration of nuclear excavation, scientists had already had considerable experience with detonations in the alluvium of the Nevada desert within the closely controlled conditions at the test site. Still to be proven was the predictability of explosions within other materials, hard rock, as in this core, or water-saturated shale, for example. Further tests and experiments were necessary to refine the technique, to take full advantage of desirable effects and to minimize others. In initiating this phase of the Plowshare program, it was assumed that most excavation projects would require cratering of hard rock, and therefore formulas to predict crater size and shape with varying explosive yields or energy and depths of burial. In designing the hard rock experiment called Sulky, scientists sought to obtain information on crater sizes with the explosive buried at depths much deeper than optimum. The 1/10 kiloton explosive was buried 90 feet deep in hard rock. When the explosive was detonated, the velocity of the rock movement was not enough to form a crater at all, but instead a mound of broken material. Not a crater, yet still valuable nevertheless in developing crater technology and mechanics. January 1968, Project Cabriolet. 2.3 kilotons buried at a depth of 170 feet in hard rock. Laboratory mathematical models, computer codes, and data from previous experiments refined and extended new predictive capabilities. The crater's actual depth was 117 feet. The radius, 181 feet. Cabriolet's success indicated the need now for data to predict the effect of higher yield explosives, yields which might be required on actual projects and in more complex geology, such as in layered or wet rock. For Project Schooner, the yield was increased to 35 kilotons, and the explosive emplaced 355 feet deep in a formation of layered rock with varying moisture content. Schooner produced a crater 208 feet deep and 852 feet in diameter. Its layered geology producing a distinctive configuration noted by its steep walls. When nuclear explosives are used to build new canals, harbors, to clear waterways, to remove overburden in surface mines or quarries, the technique used will likely be some variation of that first used in the experiment called buggy. 5 1.1 kiloton explosives in a row, 150 feet apart, buried 135 feet deep, and fired simultaneously. This was a crucial test. 6 years of research, experimentation, and data collection said the simultaneous multiple explosions, the interaction of each with its neighbor, could excavate a usable ditch or channel of predictable dimensions. Where experience with other rock formations suggested a depth of 150 feet for the explosive, the new predictive capabilities placed it instead at 135 feet. The countdown reached zero time on March 12, 1968. The experiment was termed a success and a significant step toward the use of nuclear explosives as a practical excavation tool. Computers had predicted an average depth of 65 feet and a ditch 265 feet wide. The crater was 65 feet deep and 254 feet wide. Now, there are many subtleties of cratering techniques yet to be researched. The size and the slope characteristics of craters formed in saturated rock, the relationship of crater dimension and configuration to the explosive energy, field tests at higher yields in different kinds of rock. Laboratory research will answer these and similar questions. Public health and safety are always major considerations in any experiment. Data collected in successive field and laboratory tests permits the continuous updating of our understanding of air blast, radioactivity, ground motion, and their effects. Millions of dollars and many years have been directed to developing explosives specifically designed for excavation. These explosives and related techniques in their use have reduced associated radioactivity by 100 times. The refinement of today's engineering and rigid controls and the improved design of nuclear explosives virtually guarantee the safety of every Plowshare project. The answers to nuclear cratering and excavation are not yet all in. The package is not yet a shelf item with which new dams and canals, harbors, quarries can be ordered routinely. Yet the technique is already becoming a practical approach to the task of moving huge earth masses and shaping the resulting craters. Cratering and excavation through the use of nuclear explosives. The peaceful atom, a tool to move a mountain.
To bring water and food where there is only parched earth, and people where there is desolation. To bring freedom of movement where there are imposing barriers, and commerce where nature has decreed there will be isolation. To bring forth a wealth of materials where there are vast untapped resources, and a wealth of knowledge where there is uncertainty. To perform a multitude of peaceful tasks for the betterment of mankind, man is exploring a source of enormous, potentially useful energy, the nuclear explosion. He sees the potentials and he sees the problems. To investigate both and to develop the technology that will turn potentials into realities, the United States is conducting, for the benefit of all nations, a program it calls Plowshare. Today, this scene of preparation for a peaceful nuclear explosion is at an experimental site. Tomorrow, when the potential of nuclear explosives is fulfilled, this scene will move to the site for a new harbor, canal, or mountain pass, a mine, oil field, gas reservoir, or water storage basin, or perhaps a new underground laboratory. Whatever the site, and wherever in the world it might be, the experts participating in the event will be the same as they are here: engineers, scientists, public health authorities. But eventually, the badges of national government will give way, except for control of the explosive, to the hard hats of industry and public works personnel, using this new power tool for their own applications under established safety regulations. This is the day of reality that Plowshare is working to fulfill, when it can deliver to mankind a proven tool and a proven technology. Mankind wears many faces, lined with suffering from many different hardships. But there is a basic, frustrating problem common to all. Many of mankind's pressing needs can be accomplished only by undertaking earth-breaking and earth-moving projects that are too large or too costly with today's energy systems. Man has performed useful tasks with conventional explosives for centuries, but he has recognized and lived with their limitations. He knows that a conventional chemical explosion releases the energy that bonds atoms into molecules. But he also knows now that there is a far greater source of energy within the atom itself, the energy that holds together the heart of the atom, its nucleus. This is the energy released in a nuclear explosion. Energy so enormous that man must express the yield or energy release of nuclear explosives in terms of the tons, thousands of tons, or millions of tons of TNT required to produce an equal amount of explosive energy. But in grasping the full potential of peaceful nuclear explosives, man looks not only to their great energy, but also to their relative size and cost. He sees that a 10-kiloton nuclear explosive, for example, could be as small as 15 inches in diameter and 3 feet long. The price would be about $350,000. The equivalent 10,000 tons of TNT would fill a sphere about 73 feet in diameter with a price tag of about $5 million. Furthermore, if he increases the nuclear yield 200 times, up to 2 megatons, the package is only about 2 feet greater in diameter and 7 feet longer, and the price barely doubles. To increase the yield of the TNT 200 times, he would have to increase the size of the explosive 200 times, ending up with a pile of TNT weighing 2 million tons, which would fill a coliseum twice. And at the same time, the price of the TNT would increase 200 times, up to more than $1 billion. Enormous energy, relatively inexpensive, compact and easily transportable. This is the new power tool that Plowshare would add to man's resources of useful energy, to do jobs never before practical or even possible. Man had speculated on the peaceful potentials of nuclear explosives even before using them in time of war. It wasn't until the mid-1950s, however, that definite plans began to take shape. The United States Atomic Energy Commission was already conducting the Atoms for Peace program to benefit the health and welfare of men everywhere, developing, encouraging, and supervising the peaceful uses of nuclear radiation in science, medicine, industry, and agriculture, and of nuclear power for generating electricity. In 1957, the Commission expanded Atoms for Peace with a new program, Peaceful Nuclear Explosives. The program borrowed its name from words of the prophet Isaiah, in keeping with its goal to beat the destructive blade of the nuclear sword into a plowshare that would cut deep into the earth for the betterment of all mankind. Overall technical responsibility for Plowshare is assigned to the Atomic Energy Commission's Lawrence Radiation Laboratory at Livermore, operated by the University of California. The specialized resources of other commissioned laboratories are also brought into the Plowshare effort for major research and development work. Plus the special capabilities of various government agencies, private industries, and educational institutions. The task that faces the Plowshare team is to explore and develop safe, efficient nuclear explosives and a practical, effective way to use them. Safety and technology, the two inseparable parts of the Plowshare program. To accomplish this imposing task involves more than conducting new field experiments. It involves delving deep into the storehouse of knowledge man has collected on explosive technology and safety. Centuries of mankind's experience with chemical explosions, and more than 20 years of experience with nuclear explosions. Hundreds of nuclear explosions set off in the atmosphere, in space, underwater, and underground, in a variety of climatic conditions. All of this explosive experience combines to give Plowshare the foundation for building its own specialized technology. And it provides the basis for safety standards that govern all of Plowshare's field experimentation. Before each experiment, experts in geology, seismology, hydrology, meteorology, radiobiology, and many other fields bring their specialized knowledge and equipment into the field. Working with public health authorities, they assure that the specific experiment is being conducted within accepted safety standards. This same thorough investigation will precede the actual applications of nuclear explosions wherever and whenever they may be. What are these actual applications? Some will be dramatic in their effect, as nuclear explosions move huge masses of earth in excavation jobs, reshaping the geography of the land in dimensions never before possible to meet the needs of man. Needs he can see as he struggles against the geography nature has pitted against him. The physical effects of other nuclear explosions may never be seen by the people they serve, as the explosions are set off deep underground to shatter large masses of rock in underground engineering jobs. Other nuclear explosions will be set off to harness the instantaneous release of neutrons, extreme temperatures, and enormous pressures for scientific purposes. These will influence man more indirectly. He may never realize that his daily life has been bettered by the unique research investigations made possible with nuclear explosions. These are the types of applications that Plowshare is working to make possible through research and experimentation in the laboratory and in the field. The prelude to the full scientific exploitation of nuclear explosions took place before the eyes of observers from nations all over the world. It was the first field experiment of the Plowshare program, Project Gnome, December 1961, 25 miles southeast of Carlsbad, New Mexico. A 3-kiloton nuclear explosive was detonated in a salt bed deep under the Earth's surface at the end of this 1,000-foot-long access tunnel. Several months after the Gnome event, reporters and photographers gave the world its first look at a nuclear blasted laboratory. And Plowshare experts weathered the 140-degree heat to gather first-hand information of scientific significance. But even before this actual entrance into the cavity, instruments and earth samples had provided valuable scientific data. Earth motion studies made during the Gnome explosion added to scientists' understanding of the Earth's structure throughout a large part of the United States. In a neutron physics experiment, scientists were able to capture, analyze, and measure some of the enormous quantity of neutrons released in the explosion, an important step in expanding man's fundamental knowledge of the structure of matter. Laboratory analysis of samples taken for isotope studies showed that nuclear explosions are a new potential means of mass-producing radioactive isotopes to meet the expanding needs of science, medicine, industry, and agriculture. But this was only the beginning of what promises to be one of the most significant scientific contributions of nuclear explosions. For it appears that man may now have within his reach a key to understanding many basic processes of nature. This key may be forged by a nuclear explosion. In 1964, important steps in this direction were taken in experiments with nuclear explosives specially designed to produce high-intensity neutron radiation, the specific characteristic that promotes isotope formation. In 100 millionth of a second, more neutrons were released by each explosion than could be released over decades in the most efficient nuclear reactor. The blast pumped these neutrons into targets of uranium, producing isotopes of very heavy elements beyond uranium. Eventually, Plowshare scientists hope to use these heavier elements as targets in nuclear explosions. The result could be the production of new elements never before created by man. This may be the key to answering basic questions about nature man has asked since the beginning of time. There is another question man seeks to answer, a question that raises an even more pressing problem. How can the recovery of natural resources be increased to meet man's ever-growing needs? Plowshare underground engineering may be one of the answers. Nuclear explosions deep underground break and splinter huge areas of rock. These massive effects may permit highly promising recovery of resources that have been impossible or economically impractical to extract from the earth. By digging tunnels deep into the explosive region, Plowshare teams have been able to examine and evaluate the effects of underground engineering with nuclear explosives. Effects achieved with various explosive yields in various types of rock. Industries and research institutes in the United States and in various parts of the world have recognized many potential uses for Plowshare underground engineering. They can see how nuclear explosions could increase both the total recovery and the rate of recovery of vast natural gas and oil reserves by effectively breaking the rock so that these valuable resources can flow through. They can see how copper could be extracted from the ground more efficiently as nuclear explosions shatter the surrounding rock, letting through the solutions that dissolve the copper and carry it to the surface. They can see how the huge area of broken and fractured rock could be used for receiving as well as releasing materials, for storing natural gas near its market area, for storing rainwater that could seep down underground where it wouldn't evaporate, or even for disposing of chemical waste materials to underground formations. The mining industry has seen another significant potential for underground nuclear engineering. This potential was actually demonstrated in simulated mining operations following underground nuclear explosions. Nuclear explosions would break and crush mineral deposits, perhaps more efficiently than ever before, prior to extracting the ore by conventional underground mining techniques. Minerals, natural gas, oil, water. Investigation and development continue with government and industry working hand in hand to see exactly what role Plowshare underground engineering can play in developing these valuable natural resources. There are other needs of man that can be measured in miles and acres. Miles of grueling travel over land and sea imposed by unfriendly terrain. Miles of hauling goods to distant ports. Acres of potentially rich, inhabitable land laid waste because it is cut off from civilization, or hungry, thirsty villages cut off from water that may be but a few short miles away beyond a natural barrier. Needs like these, expanding economic and social needs of an ever-expanding population, can be met only by moving huge quantities of earth efficiently and economically. For these immense projects, in areas that are relatively isolated and underdeveloped, nuclear excavation offers the potential for providing the practical, economical means. Where present land travel is awkward, costly, time-consuming, and dangerous, excavating mountain passes for highways and railroads. Where water navigation is thwarted by imposing barriers of earth, excavating canals. where commerce is stifled by forbidding shorelines, excavating harbors, for the diversion of water, cutting channels of great width and depth to carry water to areas of need. Nuclear excavation also presents great potential for industry. For example, in the quick and economic removal of earth overlying deeply buried mineral deposits. The basic task in developing plowshare excavation technology is to answer this question. In order to produce a large crater with specific dimensions in a specific earth formation, what size explosive is required and how deeply should it be buried? Conventional explosives are routinely employed for construction and mining operations. They have been used on occasion to remove massive obstructions to commerce. A few years ago, nearly 1,400 tons of chemical explosive decapitated the submerged pinnacles of Ripple Rock that had imperiled ships using the inland passage northwest of Vancouver, British Columbia. But to produce enormous craters with scientific precision, plowshare scientists must start with the blackboard, the slide rule, and the computer. They must develop new scaling laws and mathematical models for relating the results of these smaller explosions with the requirements for larger explosions, nuclear explosions in the hundreds of kilotons and the megaton ranges, which will be needed for major earth-moving projects. Computers take these mathematical models and theoretically fire nuclear explosives, giving a picture of the effects and end results expected in a particular earth formation. A major step was taken in July 1962 to develop the technology and safety requirements for the immense excavation projects toward which Plowshare is building. This was Project Sedan. The 100-kiloton nuclear explosion excavated more than 6 million cubic yards of earth in a matter of seconds. The result was a crater more than 1,200 feet in diameter, the length of 4 football fields, and 325 feet deep, the height of a 32-story building, created in less time than it takes to describe it. To clear a volume of rock the size of the Sedan crater with conventional methods would require more than 2,000 tons of chemical explosives and 25 pieces of heavy earth-moving machinery over a period of at least 6 months. Estimates like this have prompted experts to consider using nuclear explosives to do these immense tasks never before economically feasible. But as man looks to the potentials, he is not overlooking the problems. Obviously, the same characteristics that enable nuclear explosions to perform enormous useful tasks can also present hazards if they are not properly controlled, particularly in excavation projects. These potential hazards, except radioactivity, are encountered to some degree even in large chemical explosions. The results of plowshare work in controlling and limiting the radioactivity released by a nuclear explosion have been and continue to be highly encouraging. Scientists have already determined that when nuclear explosives are buried at the depth that will produce the biggest crater, a major part of the radioactivity is swallowed up in the rubble of the crater. But the most promising results have been gained by improving the design of the explosive itself and by improving emplacement techniques. Both of these specifically calculated to reduce the release of radioactivity. In the 1962 Sedan event, for example, only a small fraction of the radioactivity produced by the explosion was released to the atmosphere. If Sedan were conducted with the improved design and techniques available today, there would be even less radioactivity, and more reduction is still expected. 100-fold reduction from the radioactivity levels of 1962 through more improvement in explosive design and emplacement techniques. When this prediction is realized, it will mean that the main limitation on nuclear excavation projects will not be radiation. It will be the other potential hazards of explosions, nuclear or conventional. The ground shock, the air blast. And the dust cloud. Just as with radiation, these other safety problems are subject to control by selecting the minimum yield necessary to do the job, by thoroughly examining the local earth structure and local buildings, by timing the event for the right weather conditions, and by temporarily relocating people and livestock. Each of these potential hazards is being carefully studied to determine the exact controls that will be needed in future large-scale projects. Although single nuclear explosions to form circular craters like Sedan have been used to develop basic technology and safety requirements, far more practical value is expected from detonating nuclear explosives in rows to form long ditches. Men have visualized the uses for this type of explosion in digging enormous mountain passes and huge canals. Several projects have already been suggested to Plowshare. A typical mountain cut would be like the one suggested in California's Mojave Desert. Demands placed on railroads and trucking for faster schedules, and the motoring public's demand for greater efficiency have led to a closer examination of one of the West's major transportation arteries. Rerouting railroad and highway traffic over the most direct path through the Mojave Desert, saving countless dollars and man-hours, would mean cutting through an imposing barrier, the Bristol Mountains. It would mean excavating a mountain pass 2 miles long, moving 68 million cubic yards of earth. This project, or a similar mountain cut, would be an effective demonstration of Plowshare's potential with rows of nuclear explosives, if all of the safety requirements can be met. But there is no doubt that most applications for nuclear excavation would be not in the United States, but in other countries. The most dramatic example so far is in Central America, the blasting of a sea-level Atlantic-Pacific interoceanic canal. Studies are being planned for both conventional and nuclear excavation on 4 possible routes for such a cut across Central America to supplement and eventually replace the Panama Canal, where ships now wait long hours to strain through the narrow, complex lock system, and others can't make it through at all. Before long, it will be inadequate. Even before it was built half a century ago, the complexity and limitations of this lock-type canal were realized. Men dreamed of a sea-level canal, but it remained a dream. Plowshare may be able to make that dream a reality, and it is being considered. It is estimated that for certain routes, nuclear explosives could excavate the sea-level canal at 1/3 the cost of conventional excavation and in considerably less time. And the end result would be a much wider and much deeper channel. A nuclear-blasted route across Central America could provide a navigable channel 1,000 feet wide and up to 200 feet deep in mid-channel, offering a virtually unlimited capacity. No wonder this enormous project has so stimulated the imagination of the world. For a canal of this immensity, representing years of planning and development, complex engineering, and precise execution, would be one of the greatest civil engineering feats of all time. And so the planning and the search for more needed information go on, as Plowshare builds toward the technology needed to accomplish the proposed projects we have seen, or any other projects of equal magnitude. Basic results of peaceful nuclear explosions have been demonstrated in moving huge quantities of earth, in breaking and fracturing masses of rock deep underground, and in providing man with new scientific knowledge. But these results are still potentials, and much work remains to be done before these potentials can be turned into the realities that will serve the specific needs of men in various parts of the world. When any one of these specific applications comes to pass, whenever the time and whatever the place, it will mean that in experiments like the one being prepared for here, the technology and safety of peaceful nuclear explosions have been thoroughly developed and demonstrated. Furthermore, when nuclear explosives are chosen to do a job, it will mean they are doing a large job cheaper than could be done with conventional methods. Or, more likely, it will mean they are doing an immense job that would be impractical because of time and costs, or even impossible with conventional methods. This is the peaceful potential of nuclear explosives that the United States is developing for all mankind. In the program it calls Plowshare.